Today we'll be talking about impulse and momentum, but first we have to talk about the cart collisions post-lab. So in this lab, we analyzed videos to investigate collisions, and what we first wanted to do was take a look at how the total kinetically stored energy before a collision is related to the total kinetically stored energy after a collision. So specifically, we're interested in modeling the relationship between the total EK before and after two carts hit. So we were able to find the masses as they were labeled on the carts in the videos, and we were able to use video analysis to track the position of each cart and obtained the velocities of each cart with the slope of each part of the lines. So before we start, please just understand that when we did this lab as our classes, the video analysis app was not working so that we could define a meter as a certain number of pixels. So all of our data today is about in grams and pixels, but that doesn't really change much in terms of our analysis and what we want to get out of this lab. So first thing we want to take note of is the fact that once we plotted the total EK after versus the total EK before, we got this big mess of numbers, and on top of that we also got this slope of 0.704. So what this suggests, if you do the equation, is that there's about 70% of the EK in the system after the collision. Okay, so this y-intercept is supposed to be very close to 0 if we had the app working, but if we kind of just ignore that for a moment, we'll see that what this equation says is that the total EK after is equal to 70% of what it was before. So one thing to note, and back to our energy discussions, was that this energy has to have been stored somewhere else that we did not see in our analysis. And it turns out that this 30% of the initial EK was stored in things like thermal energy and the sound that was created from the collisions and things like that we cannot regather again as EK. So it was at this point I introduced this new quantity, mass times velocity, and we plotted those as well. It provided a slope of practically 1, which suggests that whatever this quantity is, it's the same before and after the collision. So it turns out this quantity is called momentum, which is a word we've probably all heard before, but now we have a formal definition of it in terms of our class. Momentum is a conserved vector quantity given by the object's mass times its velocity. Now this physical quantity, momentum, does not have any special units like force or energy with newtons and joules respectively. So nothing fancy in terms of units. It's just kilograms times meters per second, which are the units of mass times velocity. Now, the most important thing about momentum is that it has a direction. So unlike energy, where it's only a number, it's a scalar quantity, vectors are arrows, and if velocity is an arrow, then so is momentum. Okay, so in other words, when we're doing our math, any minus signs are going to matter a lot when we do our calculations. Now in the energy unit, we used energy flow diagrams, or LOL diagrams, to keep track of how energy is stored in a system before and after a change occurred. The process of working also helped us keep track of how much energy is transferred into and out of our system. So here we see a system where we initially have 2 joules of energy, 1 joule in EG and 1 joule in EK. And what happened here was that some type of external force must have transferred 2 joules of energy into our system, and now we have a total of 4 joules of energy in our system. So everything in terms of joules is accounted for. And we found that LOL diagrams did a nice job of organizing all of these terms and complicated calculations. Now we also have a similar way of tracking momentum before and after collisions. Here we see an energy bar graph on the left that has 12 units of energy stored in a spring as ES. Now, to the right is our new momentum charts, which show positive 12 units of momentum. Notice that momentum charts are about area rather than height. So in the energy bar graph, we cared about the height of our bar graphs of 12 joules here, but in this unit, what we're going to keep track of is the size of these rectangles in our charts. So notice that momentum charts are about area, not height. That's the first and foremost thing about these charts. On a momentum chart, each object with momentum is represented by a rectangle. Our momentum rectangles have a base of mass and a height of velocity. One key feature is that since momentum can point in the negative direction, we also have a negative place to put our momentum rectangles if an object were to be traveling in the negative direction. So if you have an object traveling in a negative direction, you should have a rectangle for that object somewhere down here. Another important thing to note is how different moving objects can have the same momenta. Small objects moving fast can have the same momentum as large objects moving slowly. Notice how the rectangle of this small mass is skinny and it's tall. So here we see Toon Link with a skinny rectangle and very tall height for his momentum rectangle, whereas Bowser here, he's a big guy, so we've got a wide base of 6 kilograms and a height of 2 meters per second. So notice, though, how all three of these characters, Adult Link, 12 kilograms times meters per second, Toon Link with 12 kilograms times meters per second for momentum, and Bowser for positive 12 kilograms times meters per second for his momentum. So they all have the same momentum, though it's just expressed differently, because pretty much there's more than one way to get to number 12 if we're talking about multiplying two numbers together. Now, in the same way that working changes the total energy in the system, we also have something called impulse, which changes the total momentum in the system. Like working, an impulse is done by an external force, and that kind of makes sense because in Unit 3, for acceleration, we know that objects don't have the same velocity at all times. And later on, last semester, we learned that in order for an object to experience a change in velocity, it's got to be accelerating. And if it's accelerating, then there has to be a net external force acting on an object. So this idea here shows up again when we're talking about impulse and changing the momentum of objects. We can derive impulse if we consider how a force changes the momentum of an object in applying Newton's second law. So in order to get a better understanding of impulse, let's just think of the scenario where we consider how a tennis racket is used during a game to change the momentum of a tennis ball. So here we have some tennis ball moving to the right with 30 meters per second. It gets hit by the tennis ball and moves left 30 meters per second. In order for this to happen, the tennis racket must have applied an impulse to the tennis ball. So let's take a look at what happens during the hit. So we can write Newton's second law here as the net force is equal to the mass of the tennis ball times its acceleration. Now what I'm going to do here is I'm going to open up my acceleration and write it in terms of dv over dt. And that's equal to the net force. So here what we're talking about is the force on the ball by the racket. All right, so we can move things around to get the change in momentum on the right-hand side by swinging over this delta t. So here I'm just going to rewrite this as F external because our system is only the tennis ball, and I'm going to swing over my time by multiplying it both sides, and if it goes on the left, we lose the one on the bottom to the right. So here on the right-hand side, what we have here, if I open up my velocity, I have v final minus v initial. And then if I distribute this m to both terms inside of the parentheses, we have mass times the velocity final minus the mass times velocity initial, and I can rewrite this as just the external force times the time that it was applied for, which for a tennis racket hitting a tennis ball is very fast, is equal to the final momentum minus the initial momentum. All right, so let's just talk about a quick example for impulse. So if we have a shopping cart that's initially at rest and we push it with a force of 4 newtons for a total of 3 seconds in the positive direction, we can determine that its impulse is 12 newtons times seconds. So notice that the units of impulse are the same as the units for momentum. So here, a newton is really just kilograms times meters per second per second. The second comes along for the party and then cancels out one of these seconds here, and we end up with units of momentum. So really, an impulse is measured in the same units as momentum. So here, when we do this calculation, which is just a matter of multiplying these two numbers together, we have that the shopping cart experienced 12 newtons times seconds of impulse. So impulse changes the momentum of an object without an external force applying an impulse to an object. Its momentum will not change, which makes sense because back in last semester we learned that an object's velocity is going to remain the same unless it experiences a net force, which will accelerate it. So in this unit, we think about it similarly to energy because we have some type of beginning momentum and some impulse happens. Whatever that impulse is, that's going to give us, when added to the original momentum, the final momentum. So in our shopping cart example, we can actually determine what the momentum of the shopping cart is after you push, because initially the shopping cart has 0 kilograms times meters per second of momentum because it was at rest, and we applied 12 newtons per times seconds of impulse, and that is equal to the final momentum of the shopping cart. So in other words, we can rewrite this again because the units of impulse and momentum are the same. We can rewrite this as the final momentum is equal to just kilograms times meters per second. The most important thing I can tell you about this unit is that you want to lean on your understanding of energy beforehand because these two concepts work so similarly with one another. All right, so let's just take a look at the most important equations for energy and momentum and stack them on top of each other. Last unit, in our LOL diagrams, we learned that whatever energy you have initially stored in the system, plus whatever working there was, and sometimes there was no working, gives you the final total energy stored in the system. In this unit, it looks very similar because in the beginning we have some total momentum and some impulse could or could not happen, whatever that is. When you take the sum, it's going to be equal to the total final momentum in that system. All right, so in other words, working and impulse really are extremely similar, and they even have similar equations, right? So both working and impulse have an external force. Working is that force times delta x. For impulse, it's that force times the time that the force was being applied for. And finally, we see that the diagrams are similar as well. The challenging part in the energy unit was keeping track of all the different types of energy storage modes because each one brought its own equation, and that was kind of tricky, right? Now, luckily, in this unit for momentum, there's only one type of momentum, and momentum is just momentum. Now, the only thing that can differ is that sometimes you have objects traveling in the positive direction, sometimes you have objects traveling in the negative direction. So just keep that in mind. You can have positive and negative momentum. And we'll learn how to use these diagrams in full in our next screencast. So that's it for today. I hope this helped, and I'll see you in class.